name's Tim Ivanic, and I'm in the West Yilgarn mapping group. Our co-workers on this study were Jack Lowry, a geochemist, and our two geochronologists, Michael Wingate and Yongjung Liu. And just a bit of background about how this became a larger project, because the first few samples from Golden Grove, which is about a 60 million year old volcanic succession with significant mineralization. We dated that back in 2013, and all these ages were almost within error of each other. So we thought, where else do you get any similar aged rocks? And we compiled a lot of ages throughout mainly the Western Yilgarn, but there are a couple of examples from the Eastern Yilgarn. At Golden Grove, we found out that this work that we have done slightly changes the stratigraphy, and you can see the history from the 1990s and how different lithologies were classified in different ways. But now we've got age control on most of them. And then this study expanded to try to obtain more ages around in this slightly older time frame from more widely in the Western Yilgarn. So kind of a long strike from Golden Grove. We do need to be careful in the Yilgarn in particular, because we have sort of problems with nomenclature. When one person refers to a terrain, they may be putting a lot of emphasis on what they believe the tectonic setting of these terrains are, and there have been 22 proposed terrains, but I don't think everybody would necessarily agree there are 22 accreted terrains that we can identify. So perhaps the use of the word structural domain may in fact be more applicable across the Yilgarn, and I think there are growing numbers of people who view it more like that. Now, I'll come on to this later, but the craton itself is really a very particular point in time, but the question is how many blocks went in to build that craton, and were any of them worthy of the name protocraton? We also need to bear in mind that the present day map section and sampling is a 2D intersection with very much 3D geology, and that we can use neodymium hafnium isotope systems to kind of gauge a more of a crustal scale integrated view of the Yilgarn craton. The basement is often enigmatic, because if we find something that looks like a high-grade gneiss aged 50 million years, we sample a volcanic rock nearby, we think that the basement should be older. In fact, it often turns out that the volcanics are older and no unconformities can be seen at present. We haven't identified any. Now, the maps in the Western Yilgarn are currently most extensive in the Meekatharra to Mount Magna area. Older mapping went across the central Yilgarn and the southern Yilgarn, and there are large gaps in this data set and places we simply haven't been. But we are starting to go in what we're now calling the gap 4. There's your historical mapping without very well constrained geochronology, unfortunately. So we need more information from there. Golden Grove was mapped in 2013, and we continued to expand that particular belt because it was a very informative set of greenstone belts, the Yalgu Singleton greenstone belt. And then in the southwest Yilgarn, we had the accelerated geoscience program, and that's building on studies starting back in probably maybe as early as 2016, where we had good coverage in terms of granitic sampling and sampling of drill core. So we made significant leaps with that interpretation last year. And there are also gaps in time that we are starting to fill. And even within these long hiatuses, there are rocks dated, be them sedimentary or volcanic, but we are starting to fill in these gaps. And before all of this recent geochron, we did know about Mount Gibson and Gossan Hill, Gossan Hill is the Golden Grove sequence. But we have now shown that there is a lot more to it than just those two formations. And there are granitic suites here, and there probably are mafic suites, but we haven't been able to date them thus far. The rock types we get are often felsic volcanics, with devitrification spots, and they range from rhyolite to dacite usually. There are basalts which haven't been dated, but they could be quite voluminous in these greenstone belts. Within the gneisses, you may have old magmatites cut by more typically aged 2680 tonalite sheets. So the old material is definitely diluted by younger granites. And you can see here again some fairly shallow dipping foliation planes and granitic sheets cutting what was probably a metabasalt, the amphibolite here. And we only know it's the basalt is old because these units are young and are as old as 2950. So as you move across the Yilgarn, here's an example in the southwest, you find different greenstone belts with different lithological assemblages. This is ignoring the TTG gneisses for now, but here, for example, we find there's the Wangan Hills there. These greenstone belts are around 3 billion years old, stretching down to Ravensthorpe. You do tend to get more basalt. You often get this dacite rhyolite unit, which is very useful because we can date it. There is quite a lot of BIF, and you get those TTGs. But if you compare it to other areas of younger greenstones in the Western Yilgarn, you find that in these packages there are less siliciclastic and ultramafic units. The Yilgarn Singleton greenstone belt in detail is a real microcosm of the whole, of most of the Western Yilgarn, with the Gossan Hill group, there's Golden Grove Mine, in yellow there, but also down at Mount Gibson, Kulanuka. And as you move from the more typical 2.8 stratigraphy in the central part of the Youanmi Terrane, you then progressively encounter more and more, especially more of these older gneisses as you go west. And this shows the extent of our dating in this particular area. And each of these belts is associated with some kind of mineralization, Golden Grove being the largest VMS deposit in the Western Yilgarn. The lithologies, as I've said, Golden Grove is mainly felsic volcanic, but in other belts there's a more even distribution of basalt, BIF, and occasional subvolcanic rocks. The gneisses, I refer to them as distal gneisses because they're separated by other rock units from these older formations. As you go through from northwest to southeast, you can see Tallering is practically in narrower terrain, but you can see that the volcanism and magmatism hops around. It doesn't really have a good geographical distribution there, and you can see the individual units we've been able to date relative to other formations, and even some units that have previously been thought to be old, we've recategorized them as this nearly 2.8 billion year stratigraphy. And there are the subvolcanic granites in many cases, which in many cases are dated. And when you look in detail at these formations in terms of their geochronology, you can see these are the synvolcanic plutons, and within analytical uncertainty of the volcanics, and TTG gneisses, even these distal ones here, are overlapping with at least some of the ages obtained elsewhere in the volcanics. The whole distribution here is biased towards Golden Grove because we've basically had a lot of sampling there. But you can see the TTG gneisses in blue kind of mirror that, and it's from about 3018, I think is the oldest age, to 2910-ish. We've had dotted through time basically magmas that may or may not have been continuously erupted, but we find that as more data comes in, these peaks tend to sort of blur out. So they're isolated felsic centres, like the Gossan Hill Formation, which is about 50 kilometres in strike length. But it's possible that some basaltic rocks interlayered locally with these formations, in these formations, these basaltic rocks probably were more widespread, because we do see very voluminous basaltic accumulations. In terms of the distribution through time, when you plot this on a map, you can see that the 3.1 to 2.9 GA ages kind of form a bit of a crescent-shaped distribution. Even, I'll come on to this later, but remember this kind of horseshoe shape, and over into the eastern goldfields, one in the Maramaya Inlier, one creeping over into the Naria. As we zoom through these, you can see the oldest ones are sort of restricted to the far west of the Yilgarn, but then as you go through time, you get fairly scatty distributions of, for example, the 2.95 magmatism. And then the younger rocks at the Honmund Formation at Lake Johnston, they are relatively tightly confined. But how much are we actually missing? We haven't sampled all these greenstone belts through here yet, and some of them are not particularly well exposed. Also, what happens at depth? Again, this is where we need isotopes. So the neodymium isotope model age distribution here, with the most recent contouring, shows granitic samples in white and their mantle extraction age in these shades. You can see the Naria contains the oldest model ages of greater than 3.5. There's another blob of it here though, and if you track this around the sort of 3.3 colour shade, you can see that the Western Yilgarn, it has this kind of dominant horseshoe kind of distribution of those ages, and the CIZ is the Q isotopic zone, where huge volumes of around 2.8 billion year old rocks have been diluting that older signal down, and where they're most voluminous, they go down to almost 2.8, which is the actual age of those rocks. Notice the similar character to parts of the Burkeville terrain, which should ring a bell from the last slide. There were a few 2.9 magmatic rocks there. And now the hafnium and zircon, just from two localities, the yellow being Golden Grove, the red being Weld Range, and the blue being the distal gneisses. And they have a quite restricted distribution in time and epsilon hafnium, where they kind of average out around about 2.96 and just above Chur, so a slightly depleted mantle would explain the majority of this data. But when you go in to the full picture and involve other material, other zircons from the Yilgarn in, for example, detrital samples, you see that there's probably more going on than a simple story like that, whereby you actually have a cluster of zircons possibly indicating that there was a depleted mantle extraction event at around about 3 billion, but then again also some magmatism would have been mixed in with Naria aged material as well, whereas if you just look at Golden Grove and the Weld Range, you would at most get back to about 3.3, and again this one coming in potentially relating to an extraction event around about 3 billion. More data is of course required to fill in that story, and there are lots of zircons. Now I just quickly want to go over Golden Grove and why that's important to the story, basically because it's a highly mineralized, it's a massive sulfide, it's highly mineralized VMS deposit. This is the Gossan from Gossan Hill, where rhyolite is being altered to hematite, and the malachite and azurite from Gossan Hill pit. It shows where it's been carbonate altered, but it's a very different deposit because of, obviously there's the stats for you, but it is, in the Archean, it would only be rivaled by Kidd Creek, which is significantly bigger, but Golden Grove does stand out, certainly in the Australian Archean record. But why, the question is, why is Kidd Creek in the Abitibi subprovince only, the province being only 700 by 300, why does that smaller province compared to the West Yilgarn have essentially five times more of these VMS deposits? Is it because we haven't explored properly in the West Yilgarn, or is it, as Houston says, the Yilgarn's rifts, were they not quite as extensive or hot, or they just possibly didn't encourage mineral endowment for some reason? The magmatism we find between 3 and 2.9 billion years, described here, is distributed in this very extensive corridor, over 800 kilometers long, possibly much wider if we think about the whole Yilgarn craton. But I'm arguing that this could fit with a rift tectonic setting because we've had the development of thick stratigraphic piles. The magmatism is prolonged. There's a scatty distribution of magmatism, which could be compatible with maybe a poorly organized rift. And it's also consistent with the juvenile mantle source characteristics, and we don't have a lot of evidence of recycling of older crust. However, I would suggest more data could change that interpretation. And we know that the story is probably not as simple as this. Who knows if we can identify a mantle plume source? We haven't linked the Komatiites strongly to these magmatic centers, but there may very well be Komatiites involved in the story. So in terms of what I'm talking about, the Yilgarn protocraton, we can define various significant age markers in the history of the Yilgarn where we saw before in the Neodymium model age map, the Narrier terrain has these very old units that could even extend some further south. Are we preserving? Are we actually seeing any volcanic rocks at this age? I don't think we have any geochron on those. So maybe we're only seeing the lower crust there. There's a huge hiatus. Then you have what I'm calling the Yilgarn protocraton, which is this big horseshoe, and it would have stretched over here potentially before the Q isotopic zone overprinted it. So then you did have a hiatus of about 100 million years, unconformities, and then all of this 2.8 to 2.74 material was deposited, possibly craton wide. There's definitely some of it over here, and there's an unconformity, but there's no magmatic hiatus. There's continued magmatism, for example, Kalgoorlie rift, if you want to call it a rift, and the late basins are deposited by about 2.67, including probably at Boddington at 2.67 as well. And cratonization, as we commonly refer to it, is at about 2.6 billion years. So that really is the history of the Yilgarn in a nutshell. So what do we do to improve on our understanding? We collect more geochemical data. We're going to test to see whether we can find evidence for mantle plume input or metasomatized mantle in the source for these rocks. And we're doing that with a fairly extensive program of geochemical sampling, and we need a lot more geochron to inform us about the full distribution of these units, and also to date some of the rocks we haven't really been able to date so far, like the mafic intrusions, and go to greenstone belts where, for example, near Southern Cross, where there seems to be interlayered, interleaved, deformed units that do contain some of this age material, and just see if we can further define that stratigraphy. And we're going to go working into the Narrier terrain in the next few years, where we examine how the field relationships change as you go from these regular looking greenstone belts in the central part of the western Yilgarn, over to more dismembered belts over in the far west and northwest, and what's the relationship between those and possible basement material.